那我就开始第二场的辩论。The opponent please propose one.
We accept.
please go ahead.
Good morning, honorable judge. Good afternoon, honorable judges and fellow competitors. This is a reporter Chen Ziqian from Team Mingdao High School. Today, I'm going to present the problem number 7, lunar cannon. And this is my outline. And this is a problem statement. Two lures are tightly held against each other around projectiles such as a plastic bar cap or bow is inserting between them close to one of the ends. When extra force is exerted on the surface of the lures, the projectile is ejected at a high speed and investigates the effect and the parameter that affect the ejection speed. And our main focus is the radius of the projectile and the force application point and the additional acceleration. So this is my demonstration video. And as you can see, when the force is applied, the projectile will be ejected at a high speed. And our observation is when there is without extra force, you can see there is only a certain deformation. Well, when there is applying another extra force, which means there are two forces applied, there will become two stages of deflection, two stages of deformation. And let's move on to a theoretical model. As you can see for the force diagram here, the diagram is symmetrical, so the vertical component of the normal force and the friction can cancel out, which means the net force is horizontal. And as the gravity is perpendicular to the net force, so we think the gravity can be ignored in our theory. And after calculating the horizontal component of the normal force and friction, I can get my equation like this. Is if I want to successfully eject my projectile, tangent beta has to be greater than the coefficient of static friction. And you can also understand the theta over here as the angle of the tangent line of the arc and the horizontal line. And in our theory, we use the deflection to describe the vertical deformation of the lures. You can also understand it as the potential energy which was stored in the lures. And if there is only one force applied, the deflection can equal to this equation and equal to the vertical deformation. Well, when there is two forces applied, the deflection can be superimposed, and after superimposed, which means I add them together, I can get the total deflection, which means it is my vertical deformation. When it is at a different point, like the point 2 and point 1, the same force can contribute to a different deflection, like the F2 with the point 1 and the point 2, it contributes to a different deflection. So as I just mentioned, the deflection can be superimposed. So after superimpose, I can get a total deflection of delta x1 and delta x2, which means the vertical deformation of the lures. And this is the equation I mentioned. The deflection can be superimposed. And you can see a negative signal here because the F1 and F2 are in an opposite direction. So there is a negative sign here. And after solving the linear equation into variables, I can get the F1 and F2 by these two equations, which means if I substitute the value of x1, x2, delta x1, and delta x2, I can get the force which was applied. So I do a small experiment to make sure that my assumption is right. You can see at this part of the lure is being fixed on the table, and on the other side, I use a force sensor to apply force on the lures. And in the middle of the lures, I stick a string on it, and using the equation of F equal to negative kx to measure how much force I applied on it. And there are my two diagrams. As these two diagrams, the theoretical data is fit to the experimental data, so I can say that my assumption is right. And let's move on to the force analysis. And this is the definition of angle. As the point 1 and the point 2 is very close in our experiment, and we have measured that the bending of the point 1 and point 2 is very small. So we can say that the arc length of the point 1 and point 2 is equal to the linear distance. And there is a definition of sine theta, cosine theta, and tangent theta. And as I just mentioned before, the successful ejection condition is tangent theta has to be greater than or equal to the coefficient of static friction. So after I substitute the value of tangent theta into my equation, I can get this equation, which means if I substitute the value of x1, which means the point I apply my force, I can get the delta x1, which means how much I should apply my force, like how deeper. And in our experiment, the x2, delta x1, and f2 are all variables. but we can all write it by the function about x2. We can all use the x2 to describe it, and this is the change of the delta x1. And after calculating the horizontal component of the normal force and the friction, and divided by the mass, I can get my acceleration like this equation. So I know that the work done by the tutor is equal to the kinetic energy of the projectile. So after I integrate both sides, I can get the velocity into this. In our experiment, the projectile is fixed at 1 centimeter from the edge of the lunar, and we assume that once the ball reaches the end of the lunar, it stops accelerating. And let's move on to your experiment. This is my experimental setup. You can be focused on this. This is my launcher. I make a launcher which makes the bisector of the lunar is horizontal. So my experiment can fit to our theory. And there are a coefficient of different friction and the Young's modulus index. And there are two experiments. The first is to discuss on the different force application points, and the second is to discuss on the different projectile radius. The first experiment, my independent variable is the different points of force application. As you can see a diagram here, the farther the force is applied from a close point, the greater the speed. Which is because if the force is applied too far, if I want to reach the successful ejection condition, I have to apply more force, and more force will contribute to a greater acceleration, and greater acceleration will contribute to a greater velocity. And as the value of x1 increase, the degree by which the increase becomes larger. And as you can see of the experiment here, the experimental value is a bit greater than the theoretical value. And when the x1 is smaller, which means the velocity is smaller, the error becomes larger. And I will explain the difference later. And the second experiment, my independent variable is a projectile's radius. As you can see, the larger radius can contribute to a greater deformation, and greater deformation can contribute to a greater velocity. And as the larger of the radius, you can find that there will become a greater arrow. And I will also discuss on this arrow later. And with a larger radius, during the pressing down phase, before reaching the successful ejection condition, the lunar gets stuck on the projectile and cannot be further pressed down. So I can find the boundary, like the pressing critical value over here, which radius will have the different boundary. And so let's move on to the discussion. This is the diagram I use in my experiment too. We can see that all of the experimental data is greater than the theoretical data. And the smaller x1, which means the smaller velocity, will have a bigger difference. And with a bigger radius, it will have a bigger radius. In our assumption, we assume that the projectile will stop accelerating once it reaches the end of the ludus. But after we look at the video of the experiment, we have found out that due to the lunar have the velocity of closing, if the velocity of the projectile isn't fast enough, it will experience an additional acceleration at the end, which means it's like this. The center of the mass has left the lunar, but it will still be accelerating. So let's look at a demonstration video again. You can see that there is an additional acceleration. So in order to fix this force equation, in order to fix this velocity equation, I use the same theoretical model, but there's a new stuff, it's L. And L1 is the distance when acceleration stops in the theory. And L2 is the distance when the projectile is entirely separated from the ludus. So after revising, I can get my delta phi into this equation. And as the value of L1 and L2, it cannot be predicted. So we can only measure the value of L1 and L2 by the video of recording of the projectiles. And after revising, I can get my final velocity into this equation. So you can see a diagram here. There there is two segments of slope, but the last segment of these two can be ignored because it is when the projectile is entirely leave the ruler, and due to the additional acceleration, there will become two segments of the slope. And the smaller the velocity, the greater the arrow. It is because the smaller velocity results in a larger L2 during the final stage of the acceleration. And the larger the radius, the larger the arrow. Due to in our discussion velocity, the velocity is due to the deflection. So the greater the radius will contribute to a greater deflection, and also the greater the velocity. And so let's move on to the deflection. Let's move on to the conclusion. The first one is the projectile's experience force because the lunar bends, and the degree of bending is relative to the force, and the larger radius and the force applied to far both result in a greater deformation, which in turn leads to a higher velocity. And since the closing speed of the lunar can be quantified, so we can only observe the moment the projectile leaves the lunar through experiment and modify its final velocity accordingly. And this is all my presentation. Thank you guys for patient listening.
Thank you. Some questions on the floor.
Okay, thank you for your report. And how do you measure the actual force you push in the ruler?
Can you say again?
How do you measure the actual force? You use the hand to.
Let me show you. We fix the string on the lunar, and we apply the force by the hand. But in order to make sure that the force is same, so we measure the length of the spring. And if the length of the spring is same, we can say that the force applied to the lunar is same.
But does it have any sensor in the?
Oh, I have. Sorry, can you say again about your question?
Do you have any sensor in the spring?
What is it?
No, or just a spring.
Oh, I have measured the deformation and used the equation of F equal to negative kx to.
Okay. Thank you. And turn to page 10.
Page 10.
Yes. The phenomenon has the phenomenon consider the no pressure ruler, and the shape of ruler will change. And do the phenomenon consider that?
You think I consider what?
The force will change the ruler. And the shape of the pole.
Yes, if the force change, the shape will change.
Yes, and do you think that will affect the energy?
Oh, I have mentioned that the deflection can be considered like the potential energy which was stored in the lunar. So after applying force, the deflection can help me to calculate how much potential energy which was stored in the lunars.
How about the ball?
You mean the projectile?
Yes.
Oh, let me show you this. Let me show you this force diagram. The force that.
Sorry. Yeah,这边好注意一些。Please go ahead.
Okay, it's a power statement. When goes under the index scan, the index and the fragment can press the equal speed in this net. Actually, if not just push the ruler, it push the ruler by push the foot that's going to the ruler. And this way you use the different size or to do explaining. And in the screen, if you use hand to push the, or you use hand to push the screen, but you can consider you can measure every time you push the same point. And then there we will focus on the side of the growth if the experiment if the result of the experiment. Okay.
You want to start please start the discussion.
Okay, the question for report, can you explain the phenomenon?
You mean explain what? The phenomena of the velocity?
Yes, how it the result of the experiment.
You mean just like explain my demonstration video? Page 9. Okay.
Yes.
Oh, this is due to when there is a same force, and due to the different point, the same force can contribute to a different deflection. But like the F1, the F1 is applied at the point 1. So after point 1, like this stuff, all of the deformation is equal to this equation. But the F2 is applied at point 2. So the deflection of the point 2 is equal to this, while the point 1 is equal to this. If you want how I get this force, I have to do some for you.
Okay. Back to the implement if they use good and how to make sure every time that the page of the
Okay, which one? I mean the page of experiment.
like this one? Is it?
My launcher. Yes.
Yes. And you measure good and how to make sure you can push at the same point of the screen.
Oh, according to the experiment, we use the high-speed camera to recording it, and we use the tracker to measure the every frame of the video. And if the length of the spring is constant, so we can say that the force is constant. The high-speed camera used is like 800 frames per second. So I think the force is constant.
Okay. Thank you.
According to my simulation.
Which data you use in the simulation?
Oh, I use this like this equation, and after I substitute the value of the like x1, x2, delta x1 and delta x2, and the m and the Young's modulus and the b, I can use Python to write my equation.
What's the data of the Young's modulus?
Okay. Oh, let me show you. This. Due to this diagram, the x-axis is the deformation and the y-axis is the force, is the applied force. is applied force. And due to the equation I mentioned, is B times E is equal to F over delta. So I can get the E index over here, and the E index is equal to the 991.7.
Sorry, thank you. For which motion you use to get the F force?
Oh, this is a ruler, and I fix the side of the ruler, and I apply force, and this is the deformation, and the force I apply is like calculating by the force sensor. It's like measured by the force sensor.
Okay. Do you know how the F force angle result the because you use the head to movement spring, and spring is the ruler, and when you push, that's the true force direction, and how you get the result of the spring.
Oh, I have like this. Sorry, let me into the page that I use. Yes, like the diagram here. We assume that the force is perpendicular to the rulers. So after but the force actually affect the projectile is the F2, and we use the cosine theta to make the F2 to find out the vertical to find out the horizontal component of the F2.
Thank you. And do you make sure the speed of the ball when you injection?
Yes. And let me turn to a page to explain it to you. As you can see here,
yes.
I have calculated the N1 and N2 and the F1 and the F2. In our theory, we assume that the normal force is same, but in the actual condition, the F1, the N1 and the N2 have a minor difference, and we have calculated this. So if the N is different, the the friction is equal to N times the coefficient of friction. So in the theoretical, it might be some rotation, but after we measure it by our video of the experiment recording, identifying that the ball is rotating like the rotating is big.
Yes. So you use the experiment to get the speed of the ball, or you use the check or the motion to measure.
Can you say again about the question?
Do you use the experiment to get the speed of the ball, or use another motion?
No, I use. Sorry, let me turn to my page. Wait for a second. I use this equation to measure the force. I use this equation to find out my velocity.
No, I mean how to get the speed of the ball.
How to give the speed of the ball?
You measure, or just like that.
Just like this equation. And I know if I know the x1 and the x2 and delta x1 and delta x2, I can substitute into an equation and get the force that was applied on the projectiles.
Okay. If you use speed to know the speed of the ball, and do you consider the motion of the ball will get the energy change?
You mean
some energy will used to change the shape of the ball?
oh, I think that because I use the equation of F equal to mass times acceleration, so I don't have to calculate that some energy lost, but I have calculated the air resistance. Do you want to see the air resistance?
Turn to your Python simulation.
Yes, my Python simulation. Sorry. Let me find it. Sorry. This is just a part of the Python. I I didn't capture all of the Python in here. I just throw this photo to let you guys know I have used the Python to simulation my data.
Okay. You see the this is the size of the cone, right?
Yes.
And we will use the different size of the cones, and there is a different
Different arrow or different acceleration.
the different contested point when you practice ruler contest the cone, they will at a different point, and how using that how it to detect the result of the experiment.
We have, just as I mentioned here, the projectile is all fixed at 1 centimeter from the edge of the lunar. The lunar is like this, and I calculate 1 centimeter here and put the projectile over here. So I think there is the same touching position.
Okay, and the experiment can screen and push the ruler, and using the distance between the screen and the ball, the different distance. Do you think that will that's the result of the experiment?
Yes, obviously, like this equation. If I change the position of the spring, which means I change the value of x1, and if I substitute into this equation, the velocity will be changed. And due to our experiment, we have measured that. And due to our experiment, my x-axis is the point which I applied in my force. So I have to do this.
And you clean the experiment, you just one motion to push to apply the extra force. And do you think you can use another motion to do you think different motion to apply the extra force, but use the same extra force? That's the result of the.
You mean if there is any alternative to apply my force?
Yes. Use other motion, different motion to push the ruler, but use same force. Use the punch and use the same force.
I have considered that if I use a bow to punch it, but the energy transforming is quite difficult. So, but if I use the spring, it's the most simple one to control my force. Due to if I use a bow to put it on it, I can make sure that every time the force is applied at the same force.
Okay. So, do you have any idea to use another structure and then you can?
You mean another material of the rulers?
Yes.
Yes.
Another material of the box.
Yes, I think it will just change the coefficient of static friction and coefficient of the kinetic friction. I think this will only change this. And I think if I change the material of the bow, the velocity will be changed.
Alright. Thank you. That's all my questions.
Thank you. Something else, please summarize your discussion in 1 minute.
Okay. I asked the reporter how to make sure the apply force, and he used the program to get the speed of the ball. He not make sure he not directly make sure the speed of the ball but it's good. He considered the distance between the spring and the ball. I think that will affect the result of the experiment.
Thank you.
it is in this experiment. This is only the assumption that I have to make sure that this two equation is right. And due to this assumption, there is no projectile between the noodles. There is only one noodles, and I only want to measure.
Okay, so how do you make sure that your external force is the same?
You mean which force?
Yes, because you use
You mean this force or which one?
the force caused by your hand.
This one?
Yes.
Oh, I measure the length of the noodle, the deformation.
But can you turn to page 30?
30. This page or 30?
30.
Oh, sorry. It's my fault.
Yes, because I think that this is done. So how can you make sure that the force will
You mean can you say it again?
this string is not straight, right?
It is.
Do you think that it will cause the angle?
In our experiment data, the spring is in constant like the straight way.
And I want to ask the component, do you think that the energy loss is important in this experiment?
Oh yes.
Do you think that what factor will cause the energy loss in this experiment?
The change of the shape of the ball change and shape of the wheel change.
Oh, because due to just what I mentioned, I'm using is the Newton's law, like F equal to the mass times the acceleration. So I think if the acceleration, I think the major impact is the acceleration. If there is like rotating or what will not contribute to the difference in acceleration. So
So did you change your ruler each experiment?
You mean what?
You change your ruler.
Yes, I have changed my ruler. Let me show you. This is the whole data because due to changing the material of the rulers, the E index and the mu-k index will be changed simultaneously. So I think I can't find a relation between the materials and the velocity. So I then discuss with the opponent.
Okay, I want to, the last question. What is the main reason that affect your experiment?
That
Will affect the velocity.
well, it's the extra force, just like the current statement. My current statement say affect an extra force, and I agreed on it.
The reason that affect the velocity. Yes. You think that is the force, extra force? The material. Okay. Thank you. That's my question. Hello everyone, I'm the reviewer, Zhongyi Xin from National Champ of Girls Senior High School, and today I'm going to review the problem number 7 river canal. And there's the problem statement above, and we can know that my main focus is the relationship between the velocity of the ball and the main factor, and the energy transformation during the ejecting process. And there's the review of the report, and we can know that about the theoretical model, the report says mention the force analysis and the effect and the equations of the motion. And I think that he analyzed each force between the ball being eject, and I think that's great. But I think there is he ignored the energy loss between her theory and didn't explain the relation between the theory and the real situation. And about the experiment and setup, he used hand to give the external force, and he had the radius and the force applied station point and the material of the ruler to become manipulated variable. And I think he didn't fix the external force because that there will be some error bar and ignore the rotation of the ball. And about the data analysis, he just had the data about the velocity of the ball. But I think he didn't clearly explain the relationship between the data trend and the theory. And about the review, about the short question, I think that there is a lack of the discussion about the data and the theory. I don't know what is the relation during this discussion. And about the case discussion during the discussion time, and the opponent say that how did you measure the force, and the reviewer say he used the equation of the motion to measure the force. But I think that the force caused by hand may create an error because the string is not straight, and then will cause the error, but the reporter didn't explain this. And about the, and my question is that what are the factors that will affect the energy load? Because I think the energy load will be really important, and it will affect the experiment data about the velocity. And I think that will be the rotation of the ball, and the permanent deformation of the ruler, and the deflection of the ruler. And the reporter just asked me about the rotate, and the opponent think that is the trend of the ruler. And about our question, what is the main reason that affect the external result? And the reporter said that will be the external force, and the opponent said that will be the material of the ruler. I think that is both correct, but I think that when we have the when we get the data, we need to consider the energy loss in this experiment. And about the missing point, I think we should have the discuss about the rotation of the ball and the permanent deformation of the ruler, because the energy loss will also affect the data, and his theory won't mention it. And there is the missing point about the relationship between the data and the theory, because I think that about the energy transformation, he said in his experiment, the ball will rotate, and the rotate will have the energy and the velocity change. He didn't mention the velocity change. The energy loss. How do the energy loss will affect the energy change? And I think that will the energy and the data line will not be that straight because the energy load is not stable. Thank you. That's all my presentation.
And the gravity is calculated in our theory, but due to the minimum value it holds, it does not really affect the upward and the downward normal force and the friction. Like there's just a bit difference between the upward and downward normal force, but I think that's just a minor force, and it cannot contribute to a great rotation. And the point is how we measure that. We apply a fixed force on the spring is by recording the deformation of the spring at every frame under a high-speed camera. And the high-speed camera is like 800 frames per second. So I think if every frame the distance of the spring is same, the force can be same. And the third one, sorry for misunderstanding the reviewer. The ruler is changed after every experiment to avoid permanent deformation. So there is not really a deformation that will cause to the different velocity. And according to Newton's second law, energy loss doesn't affect the velocity. If I use the equation of the kinetic energy equal to the 1/2 if I use the equation of kinetic energy equal to 1/2 times m times velocity square, this might well affect. But here I'm using is the Newton's second law. So I think the energy loss will not really contribute to the different velocity. They maybe will have some like air resistance or like air resistance that contribute to the like a smaller velocity. But I have to experiment to make sure that the air resistance is like pretty small. And this is all my presentation.
Thank you very much. Any questions from? You don't have to be this close.
It's my fault.
In your data and experience data and real data, I see obvious shift between the two results. So this is what the reason two results.
You mean it's after modified or before?
So you modify the results. You show me the
Like show my computer. Show the additional acceleration at part.
experience result and the theoretical result.
Yes, it will become a difference, and I have explained why. Because in our experiment, we assume that once the bow is like to this point, it will no longer be accelerating.
Yeah.
Accelerating, but according to our after we see the video of the recording of the experiment, we have found out that once the projectile is like this point, this is the ruler, it will still be accelerated. So the real data will be
Show me
bigger.
the correct data.
Up. You can see there is a red line and a gray line. The gray line is the velocity before modified, and the red line is the velocity after modified. So after I fix the data, it is like the experimental data is tightly fixed to the theoretical data. So I think that my assumption is right.
So, you always say that the energy loss is very important, but you mentioned that the main energy loss is rotation, right?
And I think that because he used a ruler,
Yes.
but when we use the ruler, I think that the deflection will also affect the energy loss because that it will affect the elastic potential energy.
Yes. So you think the energy loss is from the ruler bending? Because the ruler bend and then.
Yes, and I think the rotation will also affect.
So if you think that the rotation affect the cause the energy loss, so do you estimate how much energy loss in rotation and is it important to the result? Do you think?
I think that will because that when we use the external force to give the energy to the ball, and I think that the energy will also change to this angular velocity,
Yes,
and that will affect the eject velocity. So I think, and I also think that is strange because I think in the ideal situation the ball will not rotate. Because the normal force is the
Yes.
same, but he said the ball will.
Sorry for I'm going to answer this question. Sorry, wait for a second. And here, you can if I calculate the y value of every force, I can totally get this equation because there is still an mg for the projectile, and I have calculated that the normal force the upper normal force and the downer normal force is just like 2% error, so I think that can be ignored. And due to a bit different force, the friction here is equal to the normal force times the coefficient of friction. So the friction will be like a bit different. So it will cost you like a bit rotation, but I can't explore it by the experiment video.
Okay, thank you very much for your questions and replies. Let's find out the score. The scores for the reporters are 6, 7, 8, 8, 8. The scores for the reporters are 5, 5, 6, 5, 6. The scores for the viewer are 6, 6, 9, 7, 8. Thank you. Any comment for the?
Perhaps I can make some comment. I think in the first round and the second round, the reporter, most of you do a great job. But see, in your data, you will see two models. They are asking for consistency between your CO2 model and your experimental result. And it just seems that if you do some consistency check, you will strengthen your point. Right? And also you will better support your data and CO2 model. So this self-consistency, it seems a bit missing. First two wrong. Anyway, in general, I think you do a good job.
Thank you very much for the suggestions. Okay, then let's take another break. 15 minutes.